Good morning. This is Dr. Perumal, Professor of Chemical Engineering from Erode Engineering College. Today we will discuss about root locus method. In control theory and stability theory, the root locus method plays a vital role in determining the variation of the location of the roots with respect to the variation in the parameters such as controller gain. In the earlier classes we have discussed about the stability criteria for a control system, and also we have discussed about the Routh stability analysis. The stability criteria says any control system is said to be critical when the roots of the characteristic equation lies on the left half of the complex plane. If any one of the roots lies on the right half or on the axis, the system is said to be unstable. So if we want to say a control system is stable, so all the roots must have negative real parts. So in Routh stability analysis, we have discussed about necessary condition and sufficient condition. The Routh stability analysis was discussed based on by writing the characteristic equation in the polynomial form. If all the coefficient of the polynomial is positive, the system is stable. If any one of the coefficient is negative or 0, the system is unstable. Then next we will come to the sufficient condition. If necessary condition is satisfied, all the elements in the first column of the Routh array must be positive. If any one of the element in the Routh array is negative, the system is unstable. Now this root locus method discusses about the location of the roots of the characteristic equation and how it will vary based upon the variation in the controller gain. So now let us consider a simple feedback control system shown in the figure. The transfer function for the controller is given as G1. The transfer function for the process is denoted as G2, and we know the transfer function of the measuring element is H. Therefore, the transient response of the control system can be written as C equal to G1 G2 divided by 1 plus G into R plus G2 divided by 1 plus G into U. Here G is the product of all the transfer function connected to the loop. So G1 is the transfer function for the controller, G2 is the transfer function for the process, and H is the transfer function for the measuring element. Therefore, the characteristic equation is given as 1 plus G equal to 0. If the roots of this characteristic equation lies on the left half of the complex plane, the system is said to be stable. If it lies on the right half of the complex plane, it is unstable. So if we write this characteristic equation in terms of polynomial, then the stability analysis can be analyzed by Routh stability analysis, the sufficient condition and necessary condition. Here, the roots of the characteristic equation determines the form of response C of t to any particular forcing function, that is set point change and load point change. RT is the set point, UT is the load point. Now, we can define what is root locus. The root locus method is a graphical procedure for finding the roots of 1 plus G equal to 0 as one of the parameters of G varies continuously. The parameter which will vary is called as, normally it is the controller gain. It may be a proportional controller or proportional derivative controller or proportional integrated derivative, whatever it may be. The root locus will tells you how the roots will vary when there is a variation in the controller gain. So in control theory and stability theory, the root locus analysis is a graphical method for examining how the roots of a system change with variation of a certain system parameters, commonly a gain within a feedback system. The root locus plots the poles of the closed loop transfer function in the complex S-plane as a function of the gain parameter. That is, the root locus is a gain versus poles, a plot of gain versus poles in the complex plane. So construction of root locus. So now let us consider the control system given in the block diagram. The individual transfer function for each component of the control system shown in the figure is given as G1 equal to Kc, the transfer function G1 equal to Kc, G2 equal to 1 divided by tau 1 s plus 1 into tau 2 s plus 1, that is the transfer function for the process, and the measuring element, it is 1 by tau 3 s plus 1. Therefore, the open loop transfer function G is equal to sum of all the transfer function, that is Kc divided by tau 1 s plus 1, tau 2 s plus 1, tau 3 s plus 1. Now we return the alternate form G of s equal to K divided by s minus p1, s minus p2 and s minus p3, where K equal to Kc divided by tau 1, tau 2, tau 3. So P1 is the poles. So what is meant by poles and zeros? The roots of the numerator of the transfer function is called as zeros. The roots of the denominator of the transfer function is called as poles. Here there is no zeros in this equation. We have three poles, P1, P2 and P3. A pole of G of s is any value of s for which the Gs is approaches infinity. If s equal to P1, the denominator of the transfer function equation will become 0. Therefore, G of s approaches infinity. Therefore, P1 equal to 1 by tau 1 is a pole of G of s. The characteristic equation of the open loop transfer function is 1 plus K divided by s minus p1, s minus p2, s minus p3 equal to 0. This expression can be written as s minus p1 into s minus p2 into s minus p3 plus K equal to 0. So let the poles of the transfer function is minus 1, minus 2, minus 3. Then s plus 1, s plus 2, s plus 3 plus K equal to 0, where K equal to 6 Kc. Expanding the product of this equation gives s cube plus 6x squared plus 11s plus K plus 6 equal to 0. We obtained a third order equation. This can be solved for various values of K. So now we have given the poles minus 1, minus 2 and minus 3. You assume different values for K, you will get different values. For example, if K equal to 26.5, Kc equal to 4.41, then the equation becomes s cube plus 6s squared plus 11s plus 32.5 equal to 0. By solving this equation, we will get three roots. R1 equal to minus 5.10. The second root R2 is equal to minus 0.45 minus j into 2.5, that is a complex number. And R3 equal to minus 0.45 plus j 2.5. So here we have two complex roots and one real roots. Then assume different value for K, find the roots R1, R2 and R3, tabulate the value. Here The plot between the R1, R2, R3 and the value k in a complex plane is called root locus plot. Here we have three roots, that is minus 1.28, minus 0.95 and minus 0.45 minus z2.5 plus z2.5. So three roots have the complex number. There are three branches, root loci branches corresponding to the three roots, and that they merge or begin k equal to 0 at the poles of the open loop transfer function, that is minus 1, minus 2 and minus 3. The direction of increasing k is indicated on the arrow, indicated in the diagram by arrow. Also the values of k are marked on each locus. So the roots minus 1, minus 2 and minus 3 is plotted against k in a complex plane. The direction of k increasing is indicated by the arrows. So now let us summarize. The root locus diagram has the distinct advantage of giving at a glance the character of the response as the gain of the controller is continuously changed. The diagram reveals two critical values of k. One is at k2 where two of the roots become equal, and the other is at k3 where two of the roots are pure imaginary. It should be clear that the nature of the response Ct will depend on only on the roots r1, r2, r3. If the roots are all real, which occurs for k less than 0.39 in figure, the response will be non-oscillatory. If the two of the roots are complex and have negative real parts, k2 less than k3, the response will include damped sinusoidal terms which will produce an oscillatory response. If you adjust the controller gain such that k is greater than k3, two of the roots are complex and have positive real parts, and the response growing sinusoidally. Then rules for construction of root locus. Locate the open loop poles and zeros in the S plane. Find the number of root locus branches starts at open loop poles and ends at open loop zeros. N equal to P if P is greater than or equal to Z. N equal to Z if P is less than or equal to Z. Then third step, identify and draw the real axis root locus branches. If the angle of the open loop transfer function at a point is an odd multiple of 180 degree, then the point is on the root locus. If odd number of the open loop poles and zeros exist to the left side of a point on the real axis, then the point is on root locus branch. Therefore, the branch of points that satisfies this condition is the real axis of the root locus branch. If n, the number of poles equal to the number of branches, so n equal to p if p is greater than or equal to 0, that means if poles are greater than or equal to 0, in that case the number of branches is equal to 3. If we have 3 poles, we have 3 branches. If n equal to z, that means if p is less than, the number of poles is less than the number of zeros, the number of root locus branches is equal to z. So based upon this criteria, we have to plot the poles and gain in a complex plane. If the angle of the open loop transfer function at a point is an odd multiple of 180 degree, then the point is on the root locus. If odd number of the open loop poles and zeros exist to the left side of that means if odd numbers of poles and zeros exist on the left side of the real axis, then the point is on root locus branch. So now let us discuss how we can find the root locus branches. So find the centroid and angle of asymptotes. If P equal to 0, then all the root locus branches start at finite open loop poles and ends at finite open loop zeros. If P is greater than Z, then Z number of root locus branches start at finite open loop poles and ends at finite open loop zeros. And P minus Z number of root locus branches start at finite open loop poles and ends at infinite open loop zeros. If P is less than Z, the P number of root locus branches start at finite open loop poles and ends at a finite open loop zeros. And Z minus P number of root locus branches start at infinite open loop poles and ends at a finite open loop zeros. So sum of the root locus branches approach infinity when P is not equal to 0. So asymptotes give the direction of these root locus branches. The intersection point of the asymptotes on the real axis is known as centroid. So now we can calculate the centroid by using the formula alpha equal to sum of the real part of finite open loop poles minus sum of the real part of finite open loop zeros divided by P minus Z. The formula for angle of asymptote is theta is 2q plus 1 into 180 degree divided by P minus Z, where q equal to 0, 1, 2, 3 up to P minus Z minus 1. The rules for construction of root locus. Fifth rules. Find the intersection points of root locus branches with an imaginary axis. We can calculate the point at which the root locus branch intersects the imaginary axis and the value of k at that point by using the Routh array method and the special case 2. That means we have to use the special case 2 for determining the Routh array. By the from the Routh array calculation we can find the value. If all the elements of any row of the Routh array is 0, then the root locus branches intersects the imaginary axis and vice versa. Identify the row in which a way that if we make the first element as 0, then the elements of the entire row are 0. Find the value of k for this combination. Substitute this k value in the auxiliary equation. You will get the intersection point of the root locus branch with an imaginary axis. The sixth point, find the breakaway and break-in points. If there exists a real axis root locus branch between two open loop poles, then there will be a breakaway point in between these two open loop poles. If there exists a real root locus branch between two open loop zeros, then there will be a break-in point in between these two open loop zeros. If it is a poles break away point between the poles, if it is zeros, the in between point is called break-in point. So note, breakaway and break-in points exist only on the real axis root locus branches, so not in the imaginary axis. Follow these steps to find breakaway and break-in points. Write k in terms of s from the characteristic equation 1 plus gs hs equal to 0. Differentiate k with respect to s and make it equal to 0. Substitute these values of s in the above equation. The values of s for which the k value is positive are breakpoints. Seventh point, find the angle of departure and the angle of arrival. The formula for the angle of departure is phi d equal to 180 degree minus phi. The formula for the angle of arrival phi a is 180 degree plus phi. So now let us discuss about the root locus method, construction of root locus with an example. Let us now draw the root locus of the control system having the open loop transfer function g of s into h of s equal to k divided by s into s plus 1 into s plus 5. Step 1. The given open loop transfer function has three poles, that is s equal to 0, s equal to minus 1 and s equal to minus 5. So it does not have any zeros. So in the numerator there is no roots, only the denominator has three roots, that is s equal to 0, s equal to minus 1 and s equal to minus 5. Now we plot s equal to minus 1, s equal to 0 and s equal to minus 5 in the complex plane. So three branches arises. Between 0 to minus 1, one branch, minus 1 to minus 5, another branch. So away from the minus 5, third branch. Therefore, the number of root locus branches is equal to the number of poles of the open loop transfer function, n equal to p equal to 3. The three poles are located or shown in the above figure. The line segment between s equal to 0, s equal to minus 5, s equal to minus 5 is one branch of root locus on real axis. The other branch of root locus on the real axis is the line segment to the left of s equal to minus 5. Step 2. We will get the values of the centroid and the angle of asymptotes by using the given formula. Centroid alpha equal to minus 2 because minus 2 intersects the axis, that is called centroid. The angle of asymptote theta equal to 60, 180 and 300. The centroid are three asymptotes. The centroid and the three asymptotes are shown in the following figure. So centroid equal to 2. One asymptote is 60 degree, another is 180 degree and another one is 300 degree. Then step 3. Since two asymptotes have the angle 60 degree and 300 degree, two root locus branches intersect the imaginary axis. That is one at minus j root 5, another one is plus j root 5. There will be one breakaway point on the real axis root locus branch between the poles s equal to minus 1 and s equal to 0. By following the procedure given for the calculation of breakaway point, we will get it as s equal to minus 0.473. That is in between the 0 and minus 1. The root locus diagram for the given control system is shown in the following figure. So now let us recall what is the concept of root locus. So for a open loop system, the root locus method is a graphical procedure for finding the roots of the characteristic equation. So the characteristic equation is 1 plus g equal to 0. Here the g is the sum of the product, g is the product of all the transfer function connected in the loop, that is g1, g2 and g. So now this root locus will tells you how this values for g varies with, there is a variation in the process parameters, that is the controller gain. So controller gain is sometimes called as sensitivity. So this tells you how the sensitivity will affect the transient response. So this is the definition or concept of root locus. So to plot the root locus, we have to find the poles and zeros of the characteristic equation. The poles, what is poles and what is zeros? The roots of the characteristic equation in the numerator is called as zeros. The roots of the characteristic equation in the denominator is called poles. So when we constructing a root locus, the number of root locus branches or the loci depends upon the number of poles and number of zeros. So if the number of poles number of root locus branch is equal to number of poles. If P is greater than or equal to Z, that means if the number of poles is greater than or equal to Z, the number of root locus branch is equal to number of poles. If P is less than Z, in that case, the number of root locus branches is equal to the number of zeros. That means the number of roots in the numerator. Then the root locus diagram is plotted against the number of poles, that is the roots of the characteristic equation, and the controller gain value. So for various, if write the characteristic equation in a polynomial form and substitute the value for k, you assume different value for k and find out the R1, R2 and R3. So in this diagram, there are three roots, R1, R2 and 3. So here the k changes continuously. The direction of increasing k is indicated by the arrows in the diagram. Here we have 3 roots, minus 1.28 minus j.75, minus 1.28 plus j.75, minus 0.95 minus j1.5, minus 0.95 plus j1.5, minus 45 minus j2.5, minus 0.45 plus j2.5. So 3 roots. So when k equal to 1.58, 6.6 and 26.5, R2 and R3 are equal. When k equal to 0, we have only real number. K equal to 0.23, real number. K equal to 0.39, we have real number. Then the formula for calculating the centroid. So centroid is the point where the asymptote intersect with the real axis. So the formula for calculating centroid is alpha equal to sum of the real part of finite open loop poles minus sum of the real part of the finite open loop zeros divided by p minus z.